Okay, so a very warm good afternoon to all the participants. So now can we start for this new session? Am I audible to all? Hello?
Yes, sir.
Yes, sir. Yeah. Start.
My voice is clearly audible.
Yes, clearly audible, sir.
Okay, yeah. Okay, so in this particular lecture, basically we'll cover some advanced aspects of optical access network, that is the energy efficient optical access networks. Okay, so up to now, basically what we have covered the overview of optical communication, then some basics about the gigabit passive optical networks, then various issues with WDM, TDM networks, basic WDM concepts, etc. Okay, so now I think next few lectures will be somewhat some research oriented, and that will be useful for you. So in this, we will be covering the energy efficient optical access network. Okay, so now, yes, so these are the contents of my talk. So basically, first of all, we will be seeing an introduction or the motivation behind the energy efficient optical access network. Okay, so why basically this energy efficiency is much important. Lots of researchers are gaining concern about designing the efficient optical access network, and more particularly about the energy efficiency. Okay, then you have already have some idea about the optical access network, so I'll just give some more idea, and then we'll see how to design for the advanced, flexible, resilient, bandwidth scalable optical access network architectures. Okay, sorry, this direct intervenue capable optical access networks will not be there. So basically introductions. So in this talk, basically I will be more focusing about the resource optimization. So basically how to utilize the OLT resources optimally to reduce the energy consumption, or can say utilize resources properly. So basically at the OLT side we'll cover. Okay, so this talk will be primarily focused on OLT at central office. And so at OLT, what we can achieve? So efficient use of resources gives the reliability. Suppose there are multiple transmitters, as you already know. For the WDM systems, we have the multiple transmitters. Okay, and so we can say one transmitter for one ONU, or the dedicated transmitter for particular user or ONU. But suppose at some particular instant of time, if a particular transmitter or link is failed, then what happens to the services? So basically, this is the reliability issue. What is the reliability of the network? What happens when the transmitter is failed? Then can we switch on to the next available transmitter? Or what happens to the another transmitter that is dedicated for the particular group? We'll see the reliability, then we'll see the energy efficiency. So as I can tell you that in any network, basically the traffic is not homogeneous, it is heterogeneous. Okay, so at some particular instant of time, the network some larger traffic or larger bandwidth requirement, and at some particular time it may have some ideal situation. Okay, so for that particular ideal case, when the network is not having the active users, then we can definitely turn off the particular TRX or transmitter. Okay, to save the energy. Basically, these transmitters are fitted into kind of racks or slots, and that slot also consume power because we need to give the power to that rack or that slot. So basically, I think you must have had some idea about this from the presentation of Professor Anand Srivastava. Okay, so we have the trans receivers, and simultaneously we have the 1 Gbps trans receiver or 10 Gbps trans receiver. Okay, so suppose at some particular instant of time, if the 10 Gbps services are not required, then basically we can switch to, can we switch to the other line that is at 1 Gbps? The participants, please turn off your mic. Please, it is getting disturbed. Yes, participants, please. Yeah. Option. Just wait for some time. I'm just checking how to control the other users. Yes. So basically, can we provide the services at 1 Gbps rather than 10 Gbps, as the slot for 10 Gbps transmitter consumes more power as compared to the 1 Gbps. And as in today's first session, I just given you some idea about the transmitted power or the receiver power, what minimum power is required when we are transmitting at 10 Gbps and at 1 Gbps. So basically, if the traffic in the network is low, then why to transmit on 10 Gbps? Okay, so can we switch to the 1 Gbps? So this is the idea behind this energy efficiency. So we can optimize the transmitter, we can provide the services from the consolidated transmitter if possible. So we'll see the energy efficiency aspects, and then cost efficiency, basically the operational cost. Okay, I'm not telling about the capital expenditure capex. Okay, but definitely the OpEx can be reduced. So suppose if we are transmitting the data at 10 Gbps, then definitely it will cost more, so operational power more. So at the same time, we can switch to 1 Gbps if it is not required to transmit the data at 10 Gbps to reduce the operational expenditures. Okay, so the design or the next few architectures will be the OpEx efficient also. Okay, and then bandwidth efficiency. So bandwidth efficiency is if someone is asking it only 1 Gbps, then can we provide from 10 to 1 Gbps and vice versa. Okay, so we can optimize the bandwidth also. Okay, so these few points we'll discuss in this presentation. Yes, so need for energy efficiency. So at present, the traditional energy resources as hydrocarbon energy, nuclear, natural gases, fossil fuels, etc., provide most of the energy. Okay, and as you know, these kind of energy resources are not renewable in the nature. Okay, and these resources are limited on the earth. Okay, and if you just see the present scenario, due to this pandemic situation, COVID-19, the most of the things are moving online. As you can see, if this COVID is not there, then you and we were talking in some classroom, okay, in front to front. But basically, due to this pandemic, the things are going to be online. So, like the e-education, e-healthcare, e-shopping, whatever you can think. Okay, and due to the smart living lifestyle or smart cities, various lots of IoT applications are increasing as the things are going to become smart. So like if we are just talking about the home, then basically the smart homes, which consist of smart security systems, okay, smart control of things, or whatever you can think. But there are lots of IoT applications. So basically all these applications are demanding some kind of high speed data services. Okay, and if you just think about 10 to 15 years back, then how much applications you were using that require the internet services. Now, if you just see today's scenario, then how much applications you are requiring for in your daily day-to-day life. So suppose in 15 years back, most of the banking services were offline. We need to go to the bank to avail the services. Nowadays, the internet banking is there, the mobile apps, banking apps are also there. Okay, so lots of things are smart, or we can say there is a sudden increment in the IoT applications, or we can say the smart devices, and these devices are requiring high speed internet services. Okay, so I'm not talking about the energy that is consumed by the devices itself. Okay, that is the different aspect. So suppose the number of mobiles will increase, then definitely we need to charge the mobile. Okay, but as a service provider point of view, actually the service provider needs to have lots of energy to provide the services. Okay, so as these available energy resources are not renewable in nature, so can we think of the scenario what will happen if we just think of next 10 to 15 years? So lots of things will be there, lots of energy will be there. So these available energy resources not be able to provide this sufficient energy to the internet service provider if the things are moving simply. Okay, so we need to do something. So as hydrocarbon material, and also if you see the hydrocarbon material releases large amount of carbon dioxide, CO2, or other greenhouse gases. So that is also contributing to the global warming. Okay, so we need to worry about this energy consumption as we will save the energy, and definitely we will save our friendly environment. Okay, so in the broadband active countries like China, US, Japan, it was reported that approximately 1 to 2% of total electricity was consumed by the internet. Okay, so we need to worry. So to resolve it, what we can do? So there are maybe two solutions. So first can be the renewable energy resources should be harnessed a system or to replace the traditional energy resources as much as possible. But renewable energy resources are not omnipresent. Okay, so suppose if we are talking about the wind energy, then it is not omnipresent. We can't use the wind energy at each and every place. Similarly, the solar energy is also having some kind of limitations. Okay, but definitely we can harness, and things are moving on. Solar energy is again getting attracted. Okay, but it is some different points. So as a researcher in the field of optical network, what we can do to design the low energy components, equipments, technologies, protocols, so that will reduce the energy consumption and emit the less amount of the greenhouse gases or CO2 to save our environment. So that is the main reason behind this energy efficient optical access network, right? If we just see this energy consumption in ICT, that is the information and communication technology sector. So due to the use of current telecom applications, the energy consumption in ICT is increasing very fast. Okay, and ICT is the infrastructure that is being deployed in the smart city. So we can say in a smart city, the energy consumption is increasing. So at one time we are talking about to making the cities smart, and if the energy consumption is higher, then there is a trade-off that the CO2 and other adverse gases are in a smart city. So we can say there is a concern in the smart city also. Okay, so from the data of 2009, the energy consumption by ICT was approximately 8% of the total energy consumption and increased to approximately 15% by 2020 and continue to increase at a very rapid rate. So I don't know what is the today's figure, as the whole world is facing this pandemic situation. So it might have increased significantly. Okay, so telecommunication sector and broadband services accounts nearly 4 to 6% of the global energy consumption. Okay, so for the energy efficient network, what we can think, what we can do. So we can dimension and plan the network accordingly. So basically, this is in the initial phase. Okay, efficient network processing. So like whatever possible, we can use the passive components like what this passive optical network offer in the efficient electronic equipments. So basically, whatever the electronic equipments we are using, that must be the energy efficient. We should harness the renewable energy, and we can also try to utilize things remotely. Okay, what we can do, suppose if the wind energy or solar energy is available at some distant place, so we can install the servers there also. If server is installed there and we are using the wind energy or whatever the available renewable energy there, then we can access these resources remotely. So we can basically save some energy. And the another point, that is the efficient access network design. So this is the main topic of our focus. So introduction to access networks. So basically, passive optical network is the network that is responsible for providing the internet services to the last user. Okay, so in this we have two kinds of popular PON technology, that is the TDM PON and WDM PON technology. So if we talk about the TDM PON, then basically from the OLT we transmit some data, and we can transmit it at particular one wavelength only. Okay, and we have some passive splitter at the remote node. After transmitting the data from the fiber, then we can split the signal into the multiple paths or ports. So basically, it may be 1x32 or 64 or 16, depending on the number of users or the size of the network. So what are the advantages and benefits or challenges with this TDM PON? So basically, for TDM PON, we require only one wavelength. So if we are transmitting the data at one particular wavelength, then this one wavelength will be reaching to all the users. Okay, my cursor is basically visible to you. Participants, please. Visible to you. कर सकते हैं ना?
Yes, sir. Visible, sir.
Okay, yeah. Okay, so suppose one particular wavelength lambda 1 is coming from here, so it will come to this splitter, then it will be distributed into the 32 paths, as here it is 1 cross 32. So these 32 users can access the service at only one wavelength. So basically one transmitter would suffice to serve these 32 users. Okay, so basically it utilizes low, and this optical splitter that is very economic, low cost. So it utilizes the low cost optical splitter combiner. So basically it is the cost efficient, and any wavelength source can serve all the available users in the network. Okay, so if we can transmit the data at one wavelength or two wavelength. So suppose if we are transmitting the data at two wavelengths and we are using the splitter here. Okay, so we can transmit either at, let's say, lambda 1 at 10 Gbps and lambda 2 at 1 Gbps. So we can transmit at public 1G simultaneously. Okay. And what are the challenges? So basically this power splitter has the insertion losses that is 3.5 log of 2n, where n is the number of output ports. So ideally the loss for this optical splitter is 3 log of 2n. But when we connect this splitter practically or in field, then it has some more losses due to the connection or some other issues. So suppose if this splitter is 1 cross 2, means we are dividing the signal into two parts. There must be the loss or degradement in the power of 3 dB. 3 dB, that is half. Okay, but due to the connection issues, or there must be some reflections there, so some additional power will be there. So we generally assume 3.5 log of 2n as the loss of the optical splitter. But nowadays, with the advancement in the designing technology, we may have this optical splitter with lower losses, but not less than 3 log of 2n. 3 log of 2n must be the ideal. So it may be 3.1 or 3.2. So basically in this, we're transmitting the data at only one particular wavelength for all the users. So let's say lambda 1 that is accessible by user 1, 2, 3, 4, 32. So the data that is destined for all the users is transmitted a single wavelength. So that is, suppose if data is intended for user 2, that is also reaching to user 1 or user 3. So it is less secure, we can say, and lower effective data rates. So what does it mean? So basically, if you see the Shannon channel capacity theorem, that is C log of B log of 2 1 plus SYN signal to. Okay, so if we increase the splitting ratio, then the signal to noise ratio will decrease, and as signal to noise ratio will decrease, then channel capacity will also decrease. Okay, so this is the limitation. And if I talk about the WDM PON, then basically we can transmit the multiple wavelengths from the central office or OLT. Then we can multiplex it by WDM mux or AWG kind of thing, which I had just given you some idea in my previous lecture. And then this is transmitted and then demultiplexed at remote node. Okay, so what is happening here? So basically, suppose there are n users. Okay, so for n users, we require the n transmitters. So one transmitter is dedicated for one user. Okay, so the operating cost is somewhat higher, or we can say the CapEx expenditure is somewhat also higher, because one dedicated transmitter for one user. But the data rate is very high in this case, as the signal to noise ratio after AWG or WDM mux or demux will not decrease drastically. The AWG nowadays has the losses of almost 3 to 5 dB irrespective of the number of ports. Okay, so the losses of AWG is less, and suppose if we have 1 cross 32 splitter, then what will be the loss? So 2 to the power 5, so 3.5 into 5, that is 17.5 dB. So in case of power splitter or the TDM PON, the insertion losses are very high, so data rates are not much higher there, but here the data rates are high, lower insertion losses. And as the insertion losses are low, so the power budget is not a big issue here. But in the case of TDM PON, the power budget is the issue. Okay, so but definitely the challenges are the high cost and it is not flexible. Flexible means, so suppose we are transmitting 2 wavelengths in earlier case, so 2 wavelengths are reaching to all the users. And suppose one transmitter fails, then these users will receive the data that is transmitted at the another alternative wavelength. But what is happening in this case, this is a static kind of thing. So we are transmitting the data at transmitter 1, then it is reaching to only ONU 1 or receiver 1. Okay, if transmitter 1 fails due to some reason, then there is no way to transmit data to user 1 until or unless this failed trans receiver is recovered. Okay, so this is, we can say, the not flexible, it is static. The wavelength sharing is not possible. Okay, so basically the combination of TDM and WDM PON seems to be attractive, and I will not discuss this much more as Professor Anand Srivastava has already discussed, but I'll just give you some comparative idea about these pure TDM, pure WDM, and hybrid PON. Okay, so the insertion losses of TDM PON is high while it is low in case of WDM PON. And for the case of hybrid, it must be moderate because there are some splitters, there are some AWG. Okay, so the losses will be moderate. And security. So as a security point of view, the TDM PON is less secure and WDM PON is high secure because a dedicated wavelength is used for transmission of data to a particular user. Okay, so user 1, let's say, then only lambda 1. But what happens in case of hybrid? In case of hybrid, basically, we are not transmitting the data for all the users at one particular wavelength, but what we can say, we are transmitting the data to a group of users. So let's say there are total 132 users in the network, then only 32 users can access the wavelength lambda 1 or first wavelength in this case. Okay, so and suppose if we have total 32 users and we can have the AWG of 1 cross 4 or power splitter also of 1 cross 4. So then basically for the group of 4 users, we are transmitting only one wavelength. So that is some kind of moderate security. Okay, and flexibility. Yes, TDM PON is fully flexible as any wavelength can serve the network, or we can say any wavelength. Suppose we are transmitting 2 or 4, whatever the wavelengths, all these wavelengths are reaching to all the users. Okay, so it is fully flexible. And pure WDM PON is fully static as the wavelength is destined for some particular user will only be accessible to that user. Other user cannot access the other wavelength. Okay, and this hybrid PON provides some partial or moderate flexibility. Resource sharing is pure TDM PON, yes, possible. In WDM, no, because dedicated transmitters are there. Hybrid, yes, moderate. And cost for TDM PON low, for WDM PON high, and for hybrid it is moderate. And wavelength requirement for TDM PON it is minimum, so we can say only one wavelength can serve all the users available in the network. However, there must be the power budget fulfillability. Okay, it means the receiver must receive the powers well above the receiver sensitivity level. Okay, if the insertion losses in the link are more, then receiver will not able to receive the proper power, then will detect as noise or it will give some wrong information. Okay, and for pure WDM PON, wavelength requirement is maximum. It means suppose we have 132 users, then we need to transmit 132 wavelengths for serving the 132 users. So for pure WDM PON, we require the maximum wavelengths. For pure TDM PON, we require the least wavelength. And for hybrid, we require the moderate. So basically, nowadays, just by considering all these factors, security, flexibility, resource sharing, cost, wavelength requirement, so basically this hybrid PON is becoming attractive. Okay, and if someone is ready to pay higher and someone wants to access the dedicated services, then this WDM PON is there. And for some broadcasting applications or some low quality factor services, basically this pure TDM PON is preferred. Okay. So basically we can have two remote node kind of scenario. So suppose we have OLT at the central office and remote node 1 and remote node 2. Okay, so the splitting or the order of this remote node 1 is 1 cross m and the order of remote node 2 is 1 cross n. And we have the different network scenarios. So the value of m and n would be different. So just consider some assumptions. So let's say the value of m and n is 8, 4, 16, 4, 16, 8, 32, 8. Okay, so the total number of supported ONUs will be the mn. So that is in case of m as 8 and n is 8, 4, then total 32 users will be supported. Similarly, 64, 128 and 256 users will be there. Okay, and if we just see this cost, node cost. Okay, so we are using the splitter and we are using the AWG in some case. Okay, so it will be basically depending on whether we are using the pure TDM, pure WDM or hybrid. Okay, so for a splitter, the cost is given by this 200 plus 50 log of 2x, where x is the number of output port. Okay, so basically this data is somewhat old. So nowadays it might be possible that this component price may have reduced. Okay, but it will not be reduced significantly. So, and the AWG cost is given by 500 into 70 log of 2x. So definitely from here you can see the cost of the AWG is high as compared to the cost of the power splitter. Okay, and as if the number of ports are increasing, then the cost is also increasing. So for 4-port splitter, cost is $300. You can calculate from here. And similarly for 8, 16 and 32, the cost is given by this. And for AWG, it is somewhat higher. Okay, so if we just consider, if we are employing power splitter at both the remote nodes. Okay, so at remote node 1 and at remote node 2, if we are installing the power splitter, then it will be the pure TDM. If we are installing AWG here, then it will be the pure WDM. And if we are installing power splitter here, AWG here, or AWG here, power splitter here, then it will be the hybrid. Okay, if you just see the cost of pure TDM for different network conditions, the cost of pure remote node cost of pure TDM condition is basically least, while it is maximum for pure WDM and it is moderate for hybrid. Okay, so just calculate, I will not go deeper. So now simultaneously we need to worry about the required power budget. Okay, so we just see the insertion loss for different fiber length and for different network conditions. So the network conditions are again considered as MN as 8.4, 16.4, 16.8, 32.8, and we have considered the different fiber lengths, that is 20 kilometer, 40 kilometer, and 60 kilometer. So if I just calculate the insertion loss. So for power splitter, it is considered as 3.5 log of 2n, and for AWG, it is considered as 5. Okay. Then the insertion loss for pure TDM PON is maximum, while it is least for pure WDM PON edge. If we just consider, suppose we are just considering one case, let's say this is M edge 8 and N edge 4. Okay. So yes, so M edge 8 and N edge 4. So basically what is happening here? So if in both the ports we are connected the AWG, then there will be the 5 dB and 5 dB losses for AWG. So 2 times AWG, it means 10 dB loss for there. And if we consider the 0.2 dB per kilometer loss for fiber, so for 20 kilometer fiber, it will be 4 dB additional fiber losses. And then we are just considering 6 dB as the safety margin that will be due to the future requirements. So let's say we want to extend the link, or if there is some fault inside the link, then we may need to connect them by using the connectors or splicers. So we need to worry about that also. Okay, so 6 dB losses are considered for the safety margin. So total loss for pure WDM link is 20, while if we just calculate it for the pure TDM, so then 3.5 log of 2. So this 8 is 2 to the power 3. So it is 10.5, I think. Yes, 10.5, and for this it is 7. Okay, 7 and 10.5, it is 17.5 plus 10. So it is approximately 27.5. Okay, so for pure WDM PON, the losses are 20 dB, while for the pure TDM, the losses are 27.5 dB. Okay, so we need to worry about this. And the number of required wavelengths, so definitely for pure TDM PON, we require the least number of wavelengths, so that is 1. And for pure WDM PON, we require the maximum number of wavelengths, that is equal to the number of users. Okay, so if M8 and 4, then it is 8 cross 4. And if M32 and 8, then it is 32 cross 8, something like this. Okay, so now which multiplexing technique will be better? So suppose we need to transmit the data at 1 Gbps or 2.5 Gbps or 10 Gbps. Okay, so let me just give you some idea. As the receiver will have different receiver sensitivity at 1 Gbps, 2.5 Gbps, and 10 Gbps. Okay, it means worry about this if we are operating at 10 Gbps, because at 10 Gbps the receiver will require more received power, and simultaneously we are moving from lower distance to higher distance. Then also we need to worry because the fiber losses are increasing. Okay, and at the same time, if we are moving from lower network to the higher network, then we also need to worry. Okay, so I have tried to done some kind of optimization here basically. So we are operating at 1 Gbps, and we have the network scenario something like this, 8 cross 4, then TDM is the best multiplexing technique. So basically here, this multiplexing technique is proposed in such a way that the receiver sensitivity condition is fulfilled. Okay, we are not concerned about the cost. Definitely we are preferring the TDM PON, then cost will be there, low cost will be there. But security, we need to compromise. Okay, so if we are increasing the distance, then also TDM PON will work up to 60 kilometers. Okay, and if the network size is increased, then if we are transmitting the data of up to 40 kilometers, then TDM PON will work. For 60 kilometers, we need to switch to WDM PON. If we employ here TDM PON, then basically we will not able to receive the minimum required receiver power at the receiver. Okay. Similarly, if we are increasing the number of users and distance, so for 1 Gbps, we need to employ the WDM TDM PON. Okay, and the bracket, basically there is one number, so it indicates the number of wavelengths that is required. The wavelengths, or we can say the transmitters at the transmitter. Okay, so in this case we require the 32 transmitters, and in this case only one transmitter. And if we are working at 10 Gbps, we want to transmit the data at 10 Gbps, then what is happening? For 20 kilometer and for a very small network, 32 users, we can employ pure TDM PON. Okay, only one wavelength will suffice. But suppose if the distance is 60 kilometer and if the number of users is also increased, that is 256, then basically we need to employ this WDM or pure WDM PON, and for this we require the 256 number of wavelengths. Okay, so now there is another architecture, that is adaptive bandwidth mechanism using dual rate OLT for energy efficient WDM TDM PON. So now how we can provide the dual rate data? Okay, as suppose someone want at some particular point of time 10 Gbps data and at some another time 1 Gbps, then how we can switch without affecting the service, or we can say the transition time. Okay, so basically this is one architecture. So what is happening here? I have just given you this idea simulation of the system. Okay, so if the order of this central office AWG and remote node AWG is same, suppose there are 8 wavelengths we are transmitting from here, so we'll get the 8 wavelengths here. And if this order of this remote node AWG is also 1 cross 8, then one port will receive one wavelength. Okay, and this one wavelength is now providing the service to k number of users. Similarly, this another wavelength is providing the service to another k set of users. Okay, so only one wavelength is coming here. But suppose now we want to transmit the data at dual rate, then what we can do? So basically this must be the structure in that case. So for that case, this m by 2 must be equal to n. Okay, we must fulfill this condition. So in this case, let's say there are 8 transmitters. So 8 cross 1 AWG we are using at the central office for multiplexing, and for demultiplexing at remote node we are using the AWG is the order of 1 cross 4. So I have also given you the idea about this. Okay, so now 8 wavelengths are coming, and we need to transmit these wavelengths to the 4 ports. Okay, so now what will happen? Lambda 1 will come at this point, lambda 2 will come at this point, similarly lambda 4 will come at this point. Let's say there are only 8. Okay, so 4 wavelengths are modulated at 10 Gbps and remaining 4 are modulated, let's say, at 1 Gbps. So this will, port 1 will also receive the lambda that is modulated at 1G, then lambda 6 1G, then lambda 8 1G. Okay, so each port is receiving basically 2 wavelengths. One is at 10 Gbps and another at 1 Gbps. Okay, so depending on the traffic load in the network, so let's say if we just consider the case of some university. So during the office hours, there may be some high data rate requirement, and during the night hours or morning, early morning or late night, basically the network is almost ideal. Okay, so we can turn off the transmitters or we can switch from 10G to 1G. That means we can turn off the 10G transmitter and we can just turn on the 1G transmitter. Means we can able to provide the services to 10G or 1G depending on the network conditions. Okay, so I'll just skip. Yes, so this one. So here 193.1357, these 4 wavelengths are transmitted at 10 Gbps, and 193.9, 193.3 and 5, these are transmitted at 1 Gbps. Okay, so if these wavelengths are transmitting in this way, then basically at this point we are getting these wavelengths multiplexed. So that is the stream of wavelengths 193.1, 193.3 to 194.5 is coming at this point. So due to this 1 cross 4 AWG, we'll get here 193.1, 193.9, 193.3, 194.1. Okay, so if you just observe the black color wavelength modulated at 10 Gbps, while this red one is modulated at 1 Gbps. Okay, so this particular optical distribution network is able to receive the services at 10 Gbps or at 1 Gbps. So suppose if 10 Gbps requirement is there, then 1 Gbps transmitter is off and vice versa. And suppose, let's say at some particular point of time, there is a sudden requirement of data. Okay, then what we can do, we can turn on this 10 Gbps and 1 Gbps transmitter simultaneously. Okay, so definitely it will receive 1 Gbps more power, 11G total capacity. Okay, so this 1G can be utilized by some particular user, or we can say if suppose you want to extend the network and initially we are having this 1 cross 32 splitter, and suppose in future there is an extension of the network, then we can replace this by 1 cross 64. So we can provide the services by 1 Gbps as well as by 10 Gbps transmitter. Okay, and reliability is also there. And suppose if 1 Gbps transmitter is working in at some particular instant of time, this 193.9, the fifth trans receiver is failed, this one, then we can continue the services on 193.1. And similarly, if initially this 193.1 is working in of time, this is failed, then we can continue the services on 193.9. Definitely will not able to fulfill the bandwidth demand, that is 10 Gbps, but at least we can provide the services. There we can reduce the service disruption until the recovery of this transmitter. Okay, so this is the one feature. Or what we can do, suppose have here one interleaver, that is 100 gigahertz interleaver. Okay, so what is the purpose of this interleaver? Let me just tell you, to divert this wavelength either in this way or in this way. Okay, so if the wavelength is the odd multiple of 100 gigahertz, then that wavelength will come towards this side. So this 193.1 is odd, 193.9 is odd. So basically this interleaver is connected to, okay, so this 193.1 will come here. Okay, now if I just tune this transmitted wavelength to 193.2, then what happens? So as this is even multiple of 100 gigahertz, so this wavelength will come towards this side. So this side, and here I have connected the 2 cross 4 power splitter. So this 193.2 terahertz wavelength will appear at these 4 ports, and then again it will be combined by the different sets of interleavers. So basically, suppose we want to broadcast the data. Okay, so then just by tuning this transmit wavelength, this interleaver will divert the wavelength towards this side, so we can broadcast some common data to all the users from this single transmitter. Okay, so suppose there is some common information for all the users, then we need not to transmit that information from different transmitters. We can use only one transmitter, and similarly we can broadcast the data at 1 Gbps also. So just by transmitting 194.0 wavelength, this wavelength will be here and it will be here, something like this. Okay, so this is the broadcasting at 1 Gbps. I've already explained. This is the broadcasting at 10 Gbps. Okay. Yes, there is one more important feature. So what we can do is, suppose the wavelength spacing of this central AWG is twice as compared to sorry, this remote node AW is twice as compared to the wavelength spacing of this central office AWG. So this is having 200 gigahertz spacing, this is having the 400 gigahertz spacing. Okay, so now what is happening? So two continuous wavelengths will transmit at port 1 first, then next two, then next two, then next two. Okay, so what we will have 193.1, 193.3, then 193.5, 193.7, something like this. So now in this case, this ODN1 and ODN2 is receiving the services up to 20 Gbps, while these two are receiving the services at 2 Gbps. Okay, and if I just change the center frequency of this wavelength, then there will be some different kind of distribution. Okay, so in this case, 20 Gbps, 11 Gbps, 2 Gbps, 1 Gbps. So the distribution will be something like this. So we can dynamically change the wavelength allocation. Okay, so suppose some particular network segment is having higher traffic and some particular segment is having lower traffic, then we can basically dynamically allocate the wavelengths or change or switch the wavelengths. Okay, so this is the broadcasting at 1 Gbps with coarseness. Basically, this is called as the coarseness factor if the spacing of this is as compared to this. Okay, so in this case, we'll have this allocation, wavelength allocation will be something like 193.1357, something like this. Okay. So I'll not go in this. So basically, let me just give some idea. So let's say we have some random representative traffic pattern for a week, for Sunday, Monday, Tuesday, Wednesday, Thursday, up to Saturday. We have some different network. So if the network traffic load is below certain data rate, then we'll switch to the 1 Gbps. Otherwise, we'll use the 10 Gbps. Just by employing system for this load, this traffic pattern. Basically, this is the amount of energy that we can save on different days. Okay, so Sunday, Monday, Tuesday. So almost about 50 to 60% of the energy can be saved by employing this dual rate structure. And definitely, if this traffic pattern is changing, then this energy saving capability is also changing. But definitely, there must be some energy saving. And OPEX saving and OPEX and energy, you can say it is the same structure as there is a requirement of high energy, then there is a requirement of high cost, and at the same time, if we are transmitting the data at 10 Gbps, then we need to transmit at higher bandwidth rather than the lower bandwidth, that is 1 Gbps. So bandwidth and energy consumption will affect this OPEX efficiency. So if we are saving the bandwidth as well as the energy consumption, then definitely we are saving the operational cost also. Okay, so it is the same. So now it is another architecture, that is the flexible hybrid WDM-TDM on network with pay-as-you-grow deployment. So basically, what is happening in this architecture? So let me just give you some idea. Yes. So we have some network. Okay, and the number of users in the network initially are very less. Okay, so why to install or why to deploy it, why to lay down the whole network initially? So there must be some mechanism as pay as you grow. It means we need to install or we need to extend the network as we grow. Okay, we need not to do all the capital expenditure in the initial stage of the deployment. So I'll just give you how it is working. So basically, let's say we are having 4 modules, module 1, 2, 3, 4. All these modules are transmitting the data at 10 Gbps. Okay, and with this each module, there is one 1G transmitter also. Okay, so we can transmit the data at 10 Gbps or at 1 Gbps, depending on the requirement. Okay. So now what is happening? and it is multiplexer, and let's say these 4 transmitters are transmitting the wavelength lambda 11, lambda 12, lambda 13, lambda 14. Okay, so these are multiplexed, and then these are coming at this point. So there is one optical switch. So if the phase shift of this optical switch is 180, it means these wavelengths will appear at this point. If the phase of this switch is 0, it means these wavelengths will directly go towards this side. Okay. So now see, this is transmitting the wavelength lambda 21, 22, 23, 24. So these are appearing at this point. Lambda 31, 32, 33, 34. So these are appearing at this port. Okay. And similarly, at the fourth port, input port of AWG, we are having lambda 41, 42, 43, 44. Okay. So now the phase shift of all these switches is 180 degree. Okay. So now what is happening to this AWG or at this output port? So basically, due to cyclic property, so lambda 11 will be here, lambda 12, lambda 13, lambda 14. Similarly, here lambda 21, 22, 23, 24. So 21 will be here, 22 will be here, 23 will be here, 24 will be here. 31, 32, 33, 34. Similarly, 41, 42, 43, 44. Okay, so if you just observe, all the optical distribution network is receiving 4 wavelengths and 1 wavelength from each module. Okay, so if you just see this optical distribution network 1, so lambda 11 is from module 1, lambda 24 is module 2, lambda 33 is from module 3, and lambda 42 is from module 4. Okay, so let's say initially we have this kind of network, but yes, 1 cross k. So let's say at this point initially it is 1 cross 4. And if the number of users increases, then we can have 1 cross 8 or 1 cross 16 or 1 cross 32, whatever. Okay, so initially, let's say the number of users are less. Then what to do? So basically, there is no requirement of these 3 modules. Okay, this is all only planned, but it is not installed. Okay, we cannot, there is no requirement to install these transmitters, these things in the initially. Okay. So if you just see only this module 1 is there, so lambda 11 is here, lambda 12 is here, lambda 13 is here, lambda 14 is here. It means the only one trans module that is containing 4 trans receivers would be able to suffice to provide the services to all the available users in the network. And suppose if these optical distribution networks are growing, then what we can do? So we can install the additional module. So now we'll have 2 wavelengths, lambda 21, 22, 23, 24. So basically, we need to pay as we grow. So as the network is increasing, then we are installing additional modules. So we are getting the higher services. Okay, so this is the structure here. Yes, and suppose at some particular instant of time, optical distribution network 2, 3, and 4, these are not utilizing any service. Okay, and this optical distribution network 1 is only availing the services and grown. It means the number of users are more. Okay, then what we can do, just by switching the phase of this switch from 180 to 0. So all these wavelengths will directly move towards this point. Okay, so now whatever the wavelengths that are transmitted from this module 1 is reaching to optical distribution network 1. Okay, so we can dynamically change this wavelength allocation from all the optical distribution networks to only one optical distribution network. And there is one more additional benefit, as if the wavelengths are passing from this 4x4 AWG, then there are also some losses of this AWG, but in this case it is directly connected, so the loss problem is not there. And suppose at some particular instant of time, the optical distribution network is demanding very high data rates, then what we can do? We can have the phase shift of these switches as 180. So lambda 21, 22, 23, 24 will be distributed like 21, 22, 23, 24. So one wavelength from module 2 will be here, one wavelength from module 3 will be here, and one wavelength from module 4 will be here. So basically we are receiving total 7 wavelengths. Okay, so in this way we can provide the services up to 70 Gbps to a particular distribution network with this architecture. Please, participants, please. Okay, so this is one additional benefit. So now I'll just give you, there is some noise from the participant, please. Yes. So we are also having the 1G trans receivers. Okay, so now how this architecture is working for 1G. So basically here we are having one WDM drop filter, then 1x4 power splitter. Okay, so now we'll transmit the wavelength, let's say lambda 1, and the drop wavelength of this filter is other than the lambda 1. It means this lambda 1 will come at this point, then there is some WD adder. So here at this point we are getting lambda 1, and the phase shift of the switch is 180. So this lambda 1 will come here, so it will come here. So now 1 Gbps services are reaching to this optical distribution network 1. Similarly, this lambda 2 is reaching to this ODN 2, lambda 3 is reaching to ODN 3, lambda 4 is reaching to ODN 4. Okay, now this architecture is also having the broadcasting capability. Of course, there is some common information that needs to be broadcasted to all the available users in the network. Then what we need to do? So we'll just set the drop wavelength of this WDM filter as lambda 1. It means it will drop at this port 2. Okay, so from here it will be 1x4. So 1x4 splitter will distribute this wavelength to 4 parts. So now due to this WDM adder, this lambda 1 will appear at this point, here, here, here. So now this lambda 1 will be reaching to all the distribution network just by bypassing this 4x4 AWG. Okay, so if we have some common information, then this architecture can also broadcast that information to all the available users inside the network. Okay, so this is for the upstream direction. Yes, so this is the structure, basically what the wavelengths ODN 1, 2, 3, 4 are receiving. Let me skip. And again, for some particular traffic pattern, if we just see the energy efficiency of this architecture, then it is also in the range of 40 to 50%. Okay, so we can save some amount of energy in this case also. Yes, and if we just have some broadcasting slots in the network, so suppose we are transmitting some separate signal for separate optical distribution network, but we have some instances for which we need to transmit the common data. Then by using the broadcasting capability of the network, we can increase this power efficiency, and that is again higher. So additional 8.77% energy can be saved. Okay. So there is another architecture. Yes. Yes. So what this architecture do, basically we have 4 modules. Okay, 2 modules are working at 10 Gbps and 2 modules are working at 1 Gbps. Here remote central office 4x4 AWG, at remote node 1x2 1x2 AWG. So basically 4 wavelengths are coming at this point. So these wavelengths will be demultiplexed. 2 wavelengths will be received by each port. Okay, so one at 10G, if you just observe, one at 10G and one at 1G. So lambda 11 is at 10G and lambda 33 is at 1G. Okay, so these users are able to receive the services at 10 Gbps as well as 1 Gbps, or we can simultaneously transmit the 1G and 10G data. Okay. Now, what happens if suppose suppose if the architecture is operating at 10 Gbps, then we can definitely turn off these modules. We can provide the services from the module 1 and module 2. And if we need to transmit the data at 1 Gbps, then we will turn on the module 1 and 2. We can transmit the data by module 2 and 3 and 4. And suppose at some particular instant of time, if the network is operating with module 3 and 4, at some particular instant of time, this link failed or got disconnected, or there may be some break or whatever the reason. Okay, then what we can do, so if you just observe the users which are being supported by this module 3, that is same that are being supported by this module 1. Okay, so immediately we can switch on this module 1. So the services that are being provided by this module 3 is being taken care by this module 1. So we are handling the data by module 1. So at least we can have the service reliability. Okay, we can avoid the service disruption. And now we have the time to get it resolved. And up to that, the services or data is being transmitted by this module. Okay, and similarly, if suppose there is some particular transmitter failed, suppose instead of link, if this TRX32 or this TRX42 failed, then as you know, this 3 can be compensated by this module 1. So if we just turn on this lambda 1.4, then we can provide the service. And similarly, in case of this module 4.2, we can turn on this TRX24, or that is the transmitter 4 of module 2, then we can avail the services. So basically, this is load handling. What happens if some particular module is failed? What happens if some particular transmitter is failed? We can provide the services. So I think in this case also we can save the significant amount of energy. So now I think this is the last. So in this, basically I have just given you some idea how you can add the flexibility in the optical networks, how you can add reliability in the networks, how you can utilize the bandwidth efficiently, how you can reduce the energy consumption, and how reduce the operational cost. And there is one architecture that is having the pay-as-you-grow capability. So how that architecture provides us the opportunity to pay the initial capital expenditure as we grow. Okay, so this is what I have just give you some idea about the structures. If you have some questions, then I'm open. And my mail ID, and must have my mail ID also, because I'm just mailing you from this. If you have any concern or questions in future, then definitely you can just mail me a drop. You can drop me a mail. Yes. Participants, please. Yes, any questions?
Hello, sir.
I think yes, please. Yes, please.
Hello, sir.
Yes.
Sir, I'm Jay. Yeah, I'm Jayshlin, sir.
Yes, yeah.
Yeah, I'm computer science background.
Okay.
But network basic only I know, particularly layers and protocol concept.
Yeah.
This apti systems, how do I have to design start to end? I don't know, sir, but I can understand. But where I have to start, where I have to end, that particular parameters, how to select, how to draw, and that particulars, I don't know, sir. How to I learn, sir?
So basically, you can do one thing. Actually, as I think you are switching to this new field, right? You are just
Yeah.
trying to do some work in this optical networks. Okay. So as we are in the starting of any new technology, then basically we need to come out from the comfortable zone, and you are already ready to go out from your comfort zone. Okay. So what you can do, you just you have just installed the opti system, I think. Okay, and there is one information PDF file, I think. Okay, so there is one module. So you can, you just let me just check. What is the name of that file? Folder that is installed in your C drive. Okay, then you have, I think, 2 PDF files. So in that file, you are having the detailed, and from very starting, how to design the transmitter, how to design the link, whatever. Okay, and there are various samples that is also available in the sample libraries. So you can start from there, and once you will be aware about the various components, various libraries, then I think you will be in a situation to design the network. Yes, any other question? So I think there is no more question. So we can stop at this point. We can stop here. So now the next lecture will be from 2:30 to 4. That will be given by Professor Massimo Torrentaro, that is from University of Milano, Italy, and he is one of the great expert in this field. If you just see his profile, then he's already associated with very prominent research groups, University of Ottawa, and I think University of California, Davis. Okay, so he's one of the great personality in this field. So now I request you all to kindly attend this session from 2:30 onwards. Okay, so thank you all. So there is one question. One of my students is opting to do PhD in WDM networks. Our help. Okay, yes, definitely. This question is from, I think, Pragta Kanase, right? One of my students is opting to do PhD research in WDM networks. Your work might be helpful to face some challenges in this area. So yes, I will be ready to help you. If you want to collaborate, then also we can do something. Okay. So I will be happy to help you. Yes, definitely, no problem. So when the exam was conducted, still the exam is not conducted. It is going to be conducted. Probably will take it tomorrow, because tomorrow is the last day. Okay, so if you just see the schedule, so I think we'll consider it tomorrow either from the time slot 1:30 to 2:30, because we have 1 hour time slot, or either we can have it after the validation function. Okay, because from 2:30 to 4 we have another session, and then from 4:15 to 4:45, or probably from 4:30 to 5. Actually, I need to our coordinator, sir. What is appropriate? So after the valedictory, I think we can have the test, or if possible, then we will have the test from 1:30 to 2:30. Between this, and it will be around 20 to 30 minutes, not more than that. Okay, I will inform you about that. Yes, so thank you. And another question is image compression encryption in secured optimal network. which design is better? I'm not getting your question exactly. Basically, what is your concern? Is it related to optical network or something else? Okay, so thank you all, and let us meet again at 2:30. Thank you.